Hello, I'm Zan Gregg in Jump Development, here to talk about my favorite graph type, the smoother. Smoother is a way of cutting through the noise and seeing the general trend. I think it's a great combination of statistics and visualization to do just that. And I'm going to show a few different types of smoothers. We have a lot of choices and go work through some examples to try to understand the nuances of the differences. But first I'm going to sort of justify why smooth, or at least set it up with one example from The Economist, where not too long ago they did a piece sort of before and after a few of their charts that they'd done throughout the year where they remade them, and one of them was remade with a smoother. And that's this polling chart, which was a couple years of data polling on Brexit, and they recorded each result and connected them with just connected lines. And the remake is on the right, where they, instead of connecting the lines, they just showed the points, a little bit faded, and then showed a smoother for the general trend. So I like this technique in general, where you have the points there for context, but they're sort of faded away, so it's not quite as noisy and distracting from the main focus, which is the main trend line. There's a lot of choices, though, in how to make that trend line. Um, and that's what I'll be going through. But certainly the most obvious probably is, how smooth do you make it? You can certainly make it bumpier and still call it a smoother, or less bumpy, and it would still fit. So there is some nuance just to creating the smoother, which might be one of the reasons it's not so common. It's not as much of a plug and play kind of thing. You have to, you know, do a little work to find the right parameters. But that's what I'll be going through. So let's get into it. I'm going to talk about four types of smoothers, mainly the last two, but just for context, we'll also talk about regression, linear regression, or polynomial regression in particular. This is certainly the most common for statisticians, and it's got some nice features for differentiation and things like that. And it's practically no parameters. I guess you can count um, the power of the exponent as a parameter for whether it's quadratic or linear or whatever. Um, and so it's easy to compare. There's no parameters to tune for the most part. The big disadvantage, well, maybe it's more of a subtle disadvantage, is this action at a distance kind of concept, where since it is a global function, a change on one part of the data is going to affect another part of the data. It's going to affect the whole fit because it's all one global function. The other disadvantage might be too obvious to even mention, but it is a big disadvantage, is that not everything fits into a nice curve. Not everything is linear, not everything is quadratic or cubic or whatever tools you have. So a lot of times you see things sort of constrained into one of these models, which may be okay as a first approximation, but certainly not convincing usually as the underlying truth. So moving average is maybe the opposite from a sophistication point of view, but it is the most popular kind of smoother in the media, which is just taking the average of some small window and using that as the point in the curve. Usually it's a lagging window, so that you're averaging, say, the previous 10 intervals, and you're using that in the curve. Um, and that one's, we see that a lot with COVID data, usually with a 7-day average, since there's a day-a-week effect. Um, the one disadvantage of those lagging smoothers is that they are lagging, and so if the curve trend is going up, the curve will go up slower 7 days later, basically. So that's one issue. Another one is there are some artifacts where things like a spike, or just a single day spike, which might be um, some old data being finally recorded, or real event. But in any case, it's a single day spike, but in the data, but in the moving average, it shows as a 7-day plateau, or whatever the interval is. Um, So next we'll get into the more sophisticated smoothers. The spline is the one I use the most often, and it's constructed by a lot of cubic curves that are sort of um, fit all at once into a big model. And I think it's best to explain it by showing this blog post that a colleague of mine wrote a while back, Dwayne Hayes. And so here is some data with a cubic spline fit. And there's a smoothing parameter called lambda, which controls how stiff it is, how lumpy you're willing to tolerate. And the way that's constructed is with a bunch of these cubic fits, and they're all basically there's these intervals defined by knots, and these knot points. And between each knots, or within each knot interval, there is a cubic spline, or just a cubic polynomial fit. And those are constrained in such a way that they meet together at the edges of the knots, and they have the same slope there as well, so it's a smooth curve. And so these are all the individual cubic fits that are behind the scene, and then if you put them all together, you get the final cubic spline. So that's how the cubic spline is fit, but the real work is in the linear algebra for doing all those fits all at once in a very fast way. So it makes it so useful. Okay, and the sort of the pro and the con of that is that it is always smooth. It is always these cubic curves. None of those curves are going to be completely flat, or I mean, I guess if you can have a relatively flat thing, but not going to be any sharp corners or anything like that, which is usually okay because usually your data is, natural data usually does not have sharp corners, but it can happen with, some new law goes into effect and it categorically changes some economic variable that's being measured. In that case, really, you probably shouldn't have one smoother that fits the whole thing, but that does happen. So something to be aware of. Smoother is always going to be smooth. Finally, I'm going to cover the loess curve, which has lots of ways to spell and pronounce, but the originally started, excuse me. Next, I'm going to cover the loess curve, which has several ways to spell and pronounce. It originally started as an acronym with the W here, locally weighted scatterplot smoothing. And we've sort of forgotten about the last part of that acronym, but I think it's important to remember the origin as, scatterplot smoothing. It really was about exploratory analysis and visualization, and, sort of just helping enhance a scatter plot, a bunch of dots, to just sort of get a sense of what the trend line is through those dots, as opposed to a modeling method or something like that. Sometime after William Cleveland introduced that, he discovered that there's a word in English, or maybe German is the origin, but called loess or loess, which is a geological formation that is a smooth hillside kind of thing. So it seemed fitting to his method, so then he started using that name instead. And I've got a web page from Wikipedia of this location in the US that has this formation called the Loess Hills or Loess Hills. You can see it's got all the pronunciations here if you know IPA. And so here's the basic smooth hillside idea. So that's the geological term, just as a little diversion. And since then, the name has acquired a backronym, local regression, um, which also fits for people that like to write things all capitalized. Okay, so the method itself, though, is it's well described by the original name. It's locally weighted, and then it's linear regression within those local intervals. So I made a little illustration of that with this data set. And this is actually a data set from one of Cleveland's books. So there's the points and a loess fit through the points. And so let me bring up my illustration here. So the idea is that we've got lots of little linear fits, and they're all stitched together to form the curve. And it's not just any linear fit. Each linear fit has a neighborhood of an equal number of points. So they might not be equally spaced, but they're always an equal number of points. In this case, it's both. Um, and there's a weighting function. So for each group of points, you apply the weighting function and a linear fit, and you get this line, and you take the center point, and that's your point for your smoother. And then you do the next one, next group of points, which is overlapping, and then fit a line and get the point in the middle. That's your smooth point. Same thing, weighting, fit a weighted line, weighted fit, weighted fit. You keep doing that, and you get these points, and then you stitch them together in some manner, and you get the final smooth curve. This weighting function is called a tricube, but anything with a similar shape, that is, high in the middle and low at the sides, will work, even a Gaussian distribution. And the fit, the local fit, doesn't have to be just a straight line. It could be a quadratic or a cubic even. The quadratic will allow you to have a smaller interval and still capture curviness like that peak there. But that's the basic idea for the loess fit. Well, there is one more step, robustness passes, as described in the original specification. After it does those steps and gets a fit, then it looks at the residuals and downweights items with high far away residuals in either direction, and then does the whole process again after doing that global weighting, and then it repeats that indefinitely as it was specified in the original documents, but all software that I've seen has a fixed number of repetitions, usually just 1 to 3, and Cleveland said 3 is almost always plenty, and that's been my experience as well. But before it stabilizes, that is. And so the idea was to try to, since this was sort of exploratory analysis kind of thing, try to take away some of those likely outliers. But that's also a source of misreading loess fits, which I'll touch on with my examples. But wanted to make sure we covered that. Okay, so let's get into some of the examples. I'm going to first start with a toy example that I've made, just a constructed function. I'm using Jump's graph builder. Just going to take X and Y in here together. And I've made this function with a little bit of noise in it. There's a ramp and a flat period, and then another flat period with this step. And there's a big outlier up here. So this, by default, we're seeing a spline smoother in Graph Builder, which does a pretty good job. As I mentioned, it can only be so sharp. I can change the smoothing parameter, the lambda, to try to capture that step better, but then that introduces waviness in other places. So it's impossible to really get it completely sharp, but that's okay. That's to be expected from a smoother. You can see it more. It certainly doesn't ignore that point, but the effect of it depends on the stiffness of the smoothing parameters of the smoother in general. So that's the spline. Let's take a look at some of these others. The loess is called local kernel in Jump. It's more of a generalized loess, but the idea is the same, and this is it fits it very well, in fact, just with the default parameters, and it's ignoring this outlier because of that robustness pass. We can turn that off, and now it's going to try to follow that outlier. We can also change the bandwidth for that local neighborhood. So that's the loess fit on this data. Now let's try a moving average. This is a centered moving average, but we can see the effect that I was talking about with the spike point, basically creating this fixed interval plateau, or sort of slanted plateau in this case, that even though the data is really just one spike, you get that kind of thing. This is the moving average is centered over the resulting point. We can change that to trailing, and you can see the effect of what I was mentioning, how it sort of, as you're going up, the smoother is always a little bit behind the actual data. Especially if we make that, this is a five value interval, we can make it more, and you'll see it trailing more. So it has that disadvantage, but the advantage is it can go to the very end, which if we do a fixed centered interval, it doesn't quite go to the end. We have this trimming. We can force it to the end, which is okay in this case because it's flat, but in most cases it can't, there's nothing in the future to average, so it can't give you as good a model there. So I think that's why the trailing smoother is so popular, even though it does have that disadvantage of lagging the data. Okay, let's get into a real example. Here's a NASA plot of Earth's surface temperature, or at least the anomaly from the historical average. And they do, this sort of has both sides of the NASA, of the economist before and after. They've got the connected lines and the smoother. So of course, I like the smoother. I don't need the connected lines, but it's NASA, so they want to be extra precise, I guess. Their smoother is a loess smoother, and it looks, it looks like a reasonable smoother as far as the degree of smoothness goes. It sort of, still accomplishes the idea of seeing the general trend. So, but maybe because of the extra noise, there was a remake of that done in a Washington Post article, and they've adopted the technique more of the economist after view, which is they've downplayed the points. They're still there for context, but they're faded out a little bit, and they've added a smoother. However, they've added a moving average smoother, a 10-year moving average. So it does have the effect of, the data goes up and the line goes up, a few years later. So basically all the data is to the left of the line when it's going up. And it also has this negative effect that I experienced, which is when I first saw this, I did not even realize these yellow dots were actually temperature values for those years, because they're so far removed from the curve, and they're the different styling. I thought it was just part of the header icon or something. So I didn't. I thought that was worth trying to explore a little bit. So I got that data, and just to see what it looks like. So let's get here on the X, and we'll get that anomaly on the Y. So here's our spline smoother, which is pretty good. We can change the stiffness depending on how much we want to emphasize the short-term variation over the long-term variation. Maybe maybe there's some sunspot thing we want to try to focus on, or we just want to focus on the real super long-term thing. So that is a choice we have to make with smoothers. But I think that gives a better picture than the trailing, kind of lagging smoother. Okay, so let's next look at this recent COVID study. There's a tweet from David Robinson, where I think there may have been a lot of things wrong with this study, but one of the things he pointed out was their loess fit looked suspicious. So this was analyzing some RNA measurements in sewage and trying to correlate that with the hospital admissions. So let's, I've got the graph that's a little bit clipped here in the Twitter view. Here's the graph he's talking about. And so he's asking, the red curve doesn't seem to be affected by the high values. Those are above 150,000. So especially these two, and these are also a little high. So the curve doesn't seem to, even acknowledge those. And so he's wondered, where these outliers are moved. And he even got the data or facsimile of it and fit some loess curves and did not get the same result. So what was going on here? It was actually just that robustness pass. It wasn't any fiendishness of the researchers. They were just using a different RPROC for loess, which had robustness on by default, or maybe they were using the same one he did and turned it on. But there are some variations there. And so we can reproduce that ourselves. Here's the data, or at least my attempt to scrape that data. We have date and RNA levels. So this is just what was the red curve in that chart. And you see the spline smoother is already, it's acknowledging the outliers or the high values. I assume they're real data values and shouldn't be ignored. What was happening with the loess local kernel fit was, by default it's got robustness on. I can change the width here to make it a little more like what was in the paper. And that's basically what they had, and it's because they had robustness on apparently. But if we turn that off, now we can see a little bit more like what David Robinson saw in his attempts to reproduce it. So this robustness pass is an important feature of loess to keep in mind as you're using it. It might be on by default without you realizing it. So be careful about that. All right, finally, let's end on a more on a positive note with this ozone thickness chart. I first saw tweeted in this view, which is celebrating the progress after the Montreal Protocol around 1989, where the ozone thickness is what's on the y-axis here. It was falling, and then shortly after the protocol went into effect, it started to level off. So that was a good thing, but I had a hard time seeing that from the chart. For one thing, there was that issue with the connected line creating the extra noise, and there's also the issue of the big globe in the background trying to show the picture of Antarctica with the rainbow theme, which wasn't helping me at all. So I got this data and brought it into JMP. So let's take a look at it. Here's the data for the last many years, and let's bring a year into the X and minimum thickness into the Y. This was the measure they were looking at. And already with the default spline smoother, it looks like we've got some insightful information here. Not only did it stop going down or level off, it might be getting a little better. At least the general trend is in the positive direction. So that's something that I completely missed on the original view. I don't know if it's because of the connected line noise or because of the background image, but it was not very apparent. So that's one success for smoothers, I think. We haven't looked at the regression smoothers in our example, so let me show an example of that. If I switch to the regression element in Graph Builder, we get a linear fit by default, so that's clearly not good, but we can do let's do a quadratic fit, and at least we get the curve there. Doesn't look too bad, might be believable. So, or a cubic, even better fit, but also suspicious. With a quadratic, we were suspicious that it's really going to keep going up that fast, and the cubic, now we're suspicious is really going to take a nosedive. So I think that's one of the drawbacks of these polynomial regressions is they do necessarily impose that model on the world, but at least within the local frame, it's not too bad. This does give me a chance to show the other drawback of these regression techniques, which is the action at a distance kind of thing. So if I just take that first point, which is 194, well, first notice how at this end it's sort of tailing off. So I'm going to just change that to say 100. It is a big change, but now it completely changed the curve on the right end, even though this was all the way on the left end. And so that's that's some sense. I mean, usually it's more subtle than that, of course, but still it will shift shift the fit globally even when there is a local change. So that's the idea with the action at a distance. And that's all I've got for smoothers, and I hope you have a new appreciation of smoothers and can use them effectively. Thank you.